Hey guys, so I just wanted to give you a quick video about 2.1, which is counting principles. This should feel fairly straightforward. Because we did the odds and probability stuff already, this stuff should feel kind of familiar. A lot of the wording, a lot of the terms we use we've already done, as well as the formulas. So hopefully this should feel really easy. The whole purpose of chapter 2 is that it's about figuring out the number of different ways that things can happen, or the different number of combinations of things. It involves a lot of counting, so we're going to develop some formulas by working through some problems in order to simplify them. This is kind of the first formula we're going to develop. In this first example, there are lots of ways to figure it out. Find one that works for you. It doesn't matter. You can do a sample space, you can do a tree diagram, you can do lists, you can draw pictures, it doesn't matter. You just have to find a way of keeping track of all the different possibilities. So this one says it's Friday and you haven't done laundry since last Sunday. You got to get dressed for school and you have 2 clean pairs of pants and 4 clean shirts. They're all different colors. How many different outfits do you have to choose from? So each one of these colors is a different way of solving this. You could list them out as jeans and the shirts that would go underneath it, sweats and the shirts that would go underneath it. So there's 4 outfits using jeans, 4 outfits using sweats, 8 outfits total. You could do pants list, shirts list, match them all up. If you do, there's 4 outfits with jeans, 4 outfits with sweats, 8 altogether. You could do a tree diagram. Tree looks like this. This one maybe feels familiar because of odds and probability, but your first option is pick what kind of pants you're going to wear. Second option is pick what kind of shirts. There are 8 complete paths from start to finish, so 8 outfits. Or you could simply list them out. Jeans and a green shirt, jeans and a blue shirt, jeans and a black shirt, all the way down until you get all 8. 4 different ways of doing it, all come out with the same answer. It really doesn't matter how you figure these out. And there are obviously other ways of doing it too, so you didn't have to do it one of these 4 ways. Okay, this one, same idea. It says Sean lives in Winnipeg and this summer he's driving out to visit family in Regina and Saskatoon. So he's starting over here in Winnipeg, he's got to get to Saskatoon, but he has to go through Regina along the way. There are 3 possible routes he wants to go from Winnipeg. So this top route, the one along the middle, the one along the bottom. And there's 2 possible routes from Saskatoon he wants to take, or to Saskatoon he wants to take. How many different routes can he take from Winnipeg to Saskatoon if he has to pass through Regina first? So there's 6. He can go up along the top and along the bottom, along the top and then along the top. The green route, the red route, and then pink and then yellow. Each one of these complete paths is a different a different path, a different route than the others. So there were 6 different colors, there were 6 different routes. But what we need to notice from this example is this idea of they all had to pass through Regina. So there's sort of this first section of his trip and then a second section of his trip. And if we think about it in 2 separate sections, the Winnipeg to Regina section has 3 routes he could take. The Regina to Saskatoon has 2 different routes. And to do his complete journey, he has to go from Winnipeg to Regina, and he has to go from Regina to Saskatoon. So if we think of this as an and problem, we can take the number of ways he goes from Winnipeg to Regina, and means multiply. From Regina to Saskatoon is 2. We can multiply it out and we can get that there's 6 routes. So we could draw the routes onto the map, or we could actually multiply the 2 together, knowing we have to do this section and this section, and that and means multiply. Okay, so this is known as the fundamental counting principle. And the sort of mathy definition of fundamental counting principle is that if there are A ways to complete one task and there are B ways to complete another task, then there are A times B ways to perform both. Another way of saying that is if there's the number of ways to do A and B is the number of ways to do A times the number of ways to do B, keeping in mind that and always means multiply. So basically, the fundamental counting principle applies to any counting type problem if the different tasks are related by the word and. So just like for probabilities, and means multiply. So if we think back to that first question where there are 2 different possibilities for pants and 4 different possibilities for shirt, because they're 2 tasks related by the word and, we can use this fundamental counting principle to solve it. In order to have an outfit, you need to be wearing pants and a shirt. So 2 different types of pants, and means times 4 different shirts, 8 outfits altogether. The same for the road trip. 3 ways to get to Regina, 2 ways to get to Saskatoon. You've got to do both, so and, multiply, you get 6. This idea of them being related by the word and is the fundamental counting principle. We can do the fundamental counting principle for more than 2 tasks. We can do it for any number of tasks that we have. In this case, it says, for your bank card, you need a 4-digit PIN number. If there are no restrictions about repeating digits in your PIN, how many different possible PIN numbers are there for you to choose from? So first of all, you need to know what the digits are. The digits are the numbers from 0 to 9. So if you count them up, there's 10 of them to choose from. Okay, this is a common math fact, you just need to know it. There are 10 digits from 0 to 9. If there's no restrictions about repeating digits, it means we can repeat our numbers. So if I put a 1 in for the first number of my PIN, I could put a 1, I could put a 1, I could put a 1. There's nothing about repeats not being allowed. So in order to do something like this, we're first going to draw 4 spaces to fill because we need a 4-digit PIN number. So I always start by drawing my 4 lines. Then I need to think about how many possible numbers can go into that first space. And if I'm allowed to use all the digits from 0 to 9, there are 10 numbers to pick from. It doesn't mean that I'm putting a 10 as my first digit of my PIN number, because that's a 2-digit number. It just means there's 10 digits that I'm choosing from. For my second number of my PIN number, because I'm allowed to repeat them, there's still 10 digits, the digits 0 to 9 I could pick from, and then 10 for the third, 10 for the second. When I'm making a PIN number, I have to have a number in the first spot, and a number in the second, and a number in the third, and a number in the fourth. Otherwise, I don't have a full PIN, and means multiply. So I'm going to multiply all my possibilities together, and I'm going to get 10,000 different possibilities for 4-digit PIN numbers. Okay, so the fundamental counting principle doesn't always apply to every problem. It's specifically for AND situation where the tasks are joined. It does not work if the tasks are OR situations, when the tasks are disjointed or not connected to one another. So OR would be our union examples from our set theory. In this case, we're looking at a deck of cards. So this is just all the cards drawn out. It says count the number of possibilities of drawing a single card and getting either a black face card or an ace. If this was in color, clubs and spades would be the black face cards. There's 6 of them. Aces, there's 4 of them. 6 plus 4 is 10. So if I counted, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 cards that fit my situation. If this was a fundamental counting principle, I would have done 6 times 4. I would have got 24, which is obviously wrong. There are not 24 cards, if I actually color them or circle them or whatever, that fit being a black face card or an ace. So for OR questions, so there's an OR right here, fundamental counting principle doesn't work. Instead, we're going to add them together. Okay, this was the same for union questions, where we said you count up the number of things in A and add to that the number of things in B. This example is slightly more complicated, same deck of cards, but it says count the number of possibilities of drawing a single card and getting either a red card or a 10. So if we count them, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28 cards that are a red card or a 10. If I count them separately, my red cards are 26, my 10s are 4, 26 plus 4 is 30, not 28. The problem is, when I do that, when I count all my reds and I count my 10s, I'm counting these red 10s twice. So it says we should get 28, we get 30 because we counted the red 10s twice. This means, to get it right, we need to add all the things in group number 1 to all the things in group number 2, then subtract anything that's in both. Hopefully this does sound familiar. This is the principle of inclusion and exclusion. So we've done this already as well. Okay, so last time we saw this, we had the probabilities in front. So P of the union of A and B equals the probability of A plus the probability of B minus the probability of the intersection of A and B. Now we're talking about the number of things. So the number of things in the union of A and B is equal to the number of things in A plus the number of things in set B minus the number of elements that are in both A and B, so that intersection point. Same thing, principle of inclusion and exclusion. So if we do that for both of those card examples, if we want to do the black face cards or an ace, the number of things that are black face cards or aces are going to be the number of black face cards plus the number of aces minus the number of any black face cards that are also aces. So there were 6 face cards, 4 aces, nothing that was both, so there's 10. For the red and 10s, the number of things in the union of red cards and 10s is going to be the number of things in the red cards, the number of cards that are 10s, minus the number of red cards that are also 10s. So we've got 26 red cards, 4 10s. We're going to subtract the 2 10s that are red. That's going to give us 28. So if we have totally separate sets, we don't have to worry about the subtraction. So 10 face cards and aces were totally separate, so there's nothing to subtract. If they overlap at all, we have to subtract the overlapping things, or the ones that are in both. One nice thing about this, if you don't remember the formulas, you can always draw out the situation and figure it out that way. You don't have to use these formulas. You can draw yourself a picture, a diagram, a tree, a list, anything, and count them up. So you should be able to come up with some way of solving these, even if you can't remember the formulas. The formulas, though, are given to you on your formula sheet. They're just written in terms of probabilities instead of in terms of numbers. So you would just change the P's to N's, and then they're the same formulas. Okay, that's it for this one. Should hopefully be fairly straightforward. We will go over it in class tomorrow.